Alrighty. Hi, everybody. Thanks again for joining and tuning in to today's presentation on EIS in battery research. So I've got quite a few slides, so let's get started. All right. The first thing I want to emphasize before we start talking about electrochemical impedance spectroscopy, or EIS, in the battery field is how broad the applications of EIS can really be. So we will be talking about batteries today. I mean, everything that's usually applied to batteries is often then applied to fuel cell materials as well. But in that field, you can start probing ionic or electronic conductivities of electrodes or electrolytes. And you can also start to study interfacial behavior in those systems. But past that, there's a lot of EIS that goes into corrosion, in understanding better how basically a surface will degrade in a corrosive environment, or even in biology. There appears to be some methods that allow for basically testing between TB positive and TB negative blood samples just using EIS. So before we keep moving into this, I really want to emphasize how broad EIS is and how an understanding of EIS can really help you in do a lot of cool experiments in a lot of different fields. So basically what EIS really is it's measuring the impedance of an electrochemical system at a range of different frequencies. And so what that really means is applying an alternating current excitation to your system, and that alternating current is going to be applied over a range of frequencies throughout your measurement, and measuring the response. And in the process of measuring that response, really you're measuring the impedance, because the impedance is an alternating current phenomena. EIS plots are usually displayed in a Nyquist format here, where you plot the real component of the impedance against the imaginary component of the impedance. And you plot the points throughout all the frequencies. So high frequencies are going to give you lower impedance, and low frequencies are going to provide much more impedance. So impedance is kind of difficult to understand until you just really see it as the analog of just resistance in a direct current kind of system. So when we apply an oscillating voltage, we then measure the oscillating current response. And when we apply an excitation, this voltage, this oscillating voltage that oscillates at an angular frequency of omega, the current response will also have a frequency of omega, but it can also have a different phase shift, this theta here, which is caused by reactance, which is going to be caused by things like capacitors or inductors within our circuit. And so now that we have not just a direct current, these inductors and capacitors behave a little bit differently than just a simple resistor. And so we start to need to have a little bit more to describe the current response. So we can actually break down that impedance into two different components. So if we consider just our sort of Ohm's law in the context of an oscillating current, we can then use the terms that we just showed in the past slide, and develop this Z here, which is the magnitude of the impedance, and then this ratio of sine of omega t to sine of omega t plus theta. And that then becomes our exponential modifier on this impedance term. So then using Euler's formula, what we can really do is divide this into a real and a complex component. And these are really the components that are then graphed in an impedance plot. So our impedance is then partly composed of a real resistive part, which is, again, our analog of DC, and then this imaginary reactive part, which is the part that comes out of the fact that we're dealing with an AC excitation that then will have some sort of oscillating component. So when we start plotting our spectra, if we consider just the previous notation of having the magnitude and the angle, the sort of theta phase shift, we can plot in an Argand diagram where we plot the magnitude of our impedance and then offset by an angle theta, which corresponds to our phase shift. We always need to have proportional axes because some of the shapes that are usually shown in some of these plots require proportional axes to actually see the right type of shape. So it's important to have axes that are of the same size on both of your axes, on your X and Y. The more common method of displaying EIS data is a Nyquist plot. And in a Nyquist plot, you just plot the real and the imaginary components against one another, and you plot all the points, even or for all the frequencies. And so the tests that you might do on a lithium-ion battery are going to range somewhere between 100 kilohertz. You can even go into the megahertz range, and all the way down to potentially 100 millihertz. Please feel free to stop me at any point if you have any questions about what I've been saying so far. So I want to take a quick look at some of the sort of the theory behind these electrochemical measurements. So we can go to just the definition of a current in the context of migration of species, diffusion of species, and convection of species. So if we look at our migration term is being driven by a potential difference, which is given by this delta phi. We have one component that is driven by diffusion, where the driving force for diffusion is concentration gradients. And then in one more term, which is just convection, which is just literally movement of species that is not driven by a gradient or driven by any sort of gradient. If we consider that we have no convection in our system, and then we assume no concentration gradients, we can just use this migration term and our current term, and we can actually then simplify out this equation into just this K with the gradient of potential. And basically what this allows us to do is have a linear response between our applied potential gradient and our current. And this is really what is most important for EIS, because when we actually consider the inductance, or when we consider the impedance of the measurement, we need our impedance response to be linearly proportional to the applied potential. If we actually have a concentration gradient, which we would get if we were then to just do a direct current measurement, because we would basically force migration of certain species to one side and develop diffusion or develop concentration gradients across our sample. In that process, we then have to include our second term, our diffusion term, and our response. There's no longer a linear relationship between our current and our applied potential. As a result, you can no longer just easily backtrack out the value of the impedance. So that's why we used alternating current in these systems, because we do not want to create diffusion, or through diffusion, we do not want to create concentration gradients in our sample. And as a result, we use alternating current to stick to this linear response. So the other thing that we do is in our alternating current approach, we also use very small voltages. So to give you an idea, usually these voltages are in the order of about 10 millivolts. And the reason we do this, we can kind of get out from the Butler-Volmer electrochemical reaction kinetics. So if we consider on the left here, our term that is driving our cathodic reaction, and on the other side, our term that is driving our anodic reaction, we have exponential terms. If we look at our plot of how this equation usually looks, you can see that we have an exponential on both sides, where our applied overpotential is going to exponentially drive the current. And again, like I said, if we want to get impedance, we need a linear response. So what we can do is apply a very small overpotential, again, on the order of about 10 millivolts. And in that process, we can then Taylor expand our exponential term and make some simplifications that allow us to then cancel out basically all of the exponential terms, and we end up with a current that is linearly proportional to the applied overpotential. So what we're really doing then is, in these EIS measurements, we're applying an alternating voltage, basically a very small magnitude on the order of about 10 millivolts, to drive a current response that will allow us to get back out the impedance in our system. All right. Before I move on to equivalent circuits, does anybody have any questions on what I've said so far? No?
Sorry, can you explain why the AC causes no concentration gradient again? Sorry, I don't think I got that part.
Absolutely. So if we consider the way, so the first reason that we need to explore is why a DC would cause concentration gradient, right? So you'd have species of one charge and species of the opposite charge being driven to opposite directions. And in that process, you're generating a concentration gradient because you forced one charge species to one side and the other to another side, right? So even if you didn't have a concentration gradient initially, you've now created one by applying a DC excitation to your system. Now, if we consider an AC system, we're basically just, we drive our potential gradient in one direction and we cause diffusion a little bit, and then we drive our potential direction in the other direction. And so now we're basically just shifting everything back and forth instead of driving everything in one direction and allowing it to remain there. Does that make sense?
It's like because of that shifting, like you're not going to get that concentration gradient. Like,
exactly.
Okay. Okay, that makes sense. Thank you.
Awesome. Thank you for the question. Any other questions?
Yeah, in what cases would you want to use an Argand diagram over a Nyquist plot?
I would say rarely. The Nyquist plot is the standard in the literature. I think Argand diagrams were used in the early stages of EIS, but conventionally Nyquist plots kind of dominate the field.
Thanks.
Yeah, no problem. No more questions? All right, let's move on to equivalent circuit fitting. So this is the most important aspect of EIS in the end. The shapes of the spectra that we end up observing are really characteristic of the quote unquote circuit elements that we have within our electrochemical system. Again, we need to plot these axes proportional to one another in order to actually see the shapes that we're supposed to be seeing. But the real system that we have in our electrochemical system can be modeled by different sort of equivalent circuits. So when we start thinking about capacitance from a double layer, we can start actually using, a capacitor to potentially fit that and get some values of capacitance out. Grain boundaries tend to have a resistor to represent the charge transfer resistance between grains, but also a capacitor aspect in parallel, because you have a gap between your particles and you're sort of making a capacitor out of that process. So really the richness of the information that we can get out of EIS comes from developing these fits. Now, these fits are not trivial, and so it requires a lot of thought and a lot of justification as to why you're building these fits in this way. So let's start looking through some circuit elements. The first element that we can have is a resistor. So a resistor on a Nyquist plot is super simple because it always has the same resistance and it has no reactive component, right? So it's just going to have a zero value of the reactive component and a whatever the resistance is will be our real component of the resistor. So Z sub R equals just the resistance. On a capacitor, on the other hand, we have really no resistance. It's a purely reactive impedance. So as you can see on a real component, we actually never have any magnitude on the real component. Now, if you consider an AC frequency being applied to a capacitor, a very fast, a very high frequency will basically not have enough charge or not have enough time to charge and end up blocking the capacitor. So you end up with effectively no impedance at all, no impedance at all. At lower frequencies, though, you start to have enough time to fill the capacitor. And when the capacitor is filled, there is no more current. So as we go towards these very low frequencies, the reactive component continually increases. And so the impedance is given by this, this term here, 1 over I omega C. Okay. So now we can start putting things in series with one another. The impedances are additive. So if we consider a resistor in series with a capacitor, the first component that we're going to have is the resistor. And since all the current always has to pass through the resistor, we're always going to be offset by the value of that resistance for this resistor. So our impedance is always going to have at least R. Now, when we're at very high frequencies, again, we still have to go through this resistor, which is going to give us a resistance of R, but this capacitor is going to provide effectively no impedance to our system. And as a result, we're going to have basically no value or a zero value of our imaginary component. As we go to lower frequencies, our capacitor is going to add resistance as it charges up and resists charge transfer. And in the process, our imaginary component continually increases. If we consider a parallel element, though, the parallel element is a little bit different. Now, the parallel element, what you need to consider is that a current is going to take the easiest path it possibly can. So at very high frequencies, if I drive a current through this system, the resistor is going to provide a lot more resistance than my capacitor will. And so as I'm at very high frequencies, my capacitor is not charging. And so effectively, all of my current is actually just going through my capacitor. The capacitor, again, provides effectively no resistance compared to the constant R of the resistor. And so it just drives straight through there preferentially. And that's what we see at high frequencies. We basically have zero value, zero impedance because we're just going straight through this capacitor. Now, on the other side, as we go to very low frequencies, our capacitor is going to fill up and effectively block any sort of charge transfer across that value. So what we have at very low frequencies is our current basically entirely going through our resistor. And we can see that at very low frequencies, we have a resistance of R that we see. Now, in between those values, you basically end up with a sort of balance between the two. At high frequencies, again, we are preferentially going through the capacitor, but after a while, after we reach this characteristic frequency F star, the capacitor or the resistor will start to take more and more of the current going through it until we ultimately hit all of the current going through the resistor. Now this sort of circuit component is quite common in equivalent circuit modeling, because like I said, this can model something like a grain boundary, where in a grain boundary can have a charge transfer resistance as well as a certain level of capacitance, and those things happen in parallel with one another. So this type of circuit is quite important for equivalent circuit modeling. Yes, so we're here. Yes, so basically when we consider charge transfer, we need to have this resistor representing the charge transfer, but also we can have a sort of double layer capacitance happening at that interface that ultimately is modeled by this capacitor that we have as well. Our characteristic frequency can then be used to basically back out what we consider to be a time constant. So a time constant for whatever process this equivalent circuit is fitting, whether it be grain boundaries, whether it be bulk conduction, all of these things are possible. And so the time constant then affects the order in which these elements appear. So if you have a few of these in series, a longer time constant, or basically a lower frequency, will get you further out here, and a higher frequency or a smaller time constant will get you down here. Now, another component that's used quite commonly is the constant phase element. It's an invented circuit element, but it's used because in a lot of instances we have very imperfect capacitors. So we actually end up with a certain offset relative to what we're supposed to see. Remember that in a capacitor, we're supposed to see a straight line with no value of real impedance, but in some circumstances, we actually end up with a certain amount of real resistance showing up. And this is because this is deviations from an ideal capacitor. And so we the degree to which this constant phase element deviates from ideality is characterized by this value of n. And in the case of n equals 0, we just end up with basically 1 over Q naught, which is our capacitor. Or no, sorry. With n equals 1, we end up with a perfect capacitor, as we saw from this equation here, where our capacitor, our impedance from a capacitor is 1 over I omega c. And so that's what we see here. As n goes to 1, we end up with an ideal capacitor, but we can basically move off of this n equals 1 in order to measure basically non-idealities. When we have a resistor in parallel with a constant phase element, we basically end up with a sort of depressed semicircle that isn't actually a full semicircle like we saw in these cases. Instead, it sort of appears like it almost starts lower. Some last components that I want to talk about, this sort of Warburg impedance, which is used to model semi-infinite one-dimensional diffusion. And this impedance basically is just a constant phase element with n equals 0.5. And so this component allows us to basically back out some diffusion coefficients within our system. And we basically get slightly different diffusion according to whether or not we have a blocking boundary. You can consider that at very low frequencies, once again, we can be driving diffusion. And in that process, we're going to start realizing that we're up against a wall with this blocking boundary, which is effectively just a capacitor. And so that's why our impedance just precipitously goes up into the imaginary values. Whereas if we're going through an infinite layer, our diffusion is not being blocked. And as a result, we end up again with this behavior that resembles the this parallel element here. Okay. Now, one question you might have is why do we examine this range of AC frequencies? And the reason is we need to apply a bunch of different frequencies in order to separate out different sort of electrical relaxation times and time constants that correspond to different regions of our sample. Now, again, as we said, our tau is a function of our F star, which represented our sort of characteristic frequency, the top of the semicircle that we developed from having a capacitor in parallel with a resistor. And what we can see is that in this plot here of a impedance spectra for calcium aluminum oxide, we see that we end up with two semicircles. Now, the two semicircles, like we said, will have different time constants. And the reason that we have different time constants is because the capacitance associated with each of these sort of electrochemical components of our system are very different. The capacitance of our bulk is quite different from the capacitance of our grain boundaries. And so in this process with EIS, we can separate out bulk and grain boundary contributions to ionic conduction through our system based on the fact that they have very different capacitances and their time constants end up quite different. So different frequencies will probe them more or less. Now, there's a lot of different components of a circuit that we can sort of separate out. Like we said, we showed the bulk and the grain boundaries, but past that, there's quite a few different other systems that are possible to probe within your EIS setup. So that's why we apply such a broad range of frequencies. By applying a really broad range of frequencies, we can really separate out different regions of whatever electrochemical sample we're characterizing, and in the process, learn about the independent contributions of different aspects of our sample. So with that, I want to ask, are there any other questions on this side of things? No questions? Okay. So now let's talk about what does it look like to actually measure an impedance spectrum in the lab. So thank you to Rebecca Vincent for this slide here. Here, basically, what we can see is that in a temperature-controlled chamber, we've assembled our impedance cell. So our impedance cell has inputs on top and on bottom with this stainless steel, these two stainless steel electrodes that are connected to either a potentiostat or frequency analyzers. A lot of biologic potentiostats are also able to do electrochemical impedance spectroscopy. So that's great. Other instances, you need to use a frequency analyzer to be able to apply these alternating currents and record the measured current. So our sample ends up being just a 6 millimeter pressed pellet from powder that we put into this impedance cell. And this sort of casing here is Delrin plastic that we then apply vacuum grease to the top and the bottom down here in order to actually seal it and make it airtight. By the way, all of this sample prep occurs within the glove box, at least for me. And we close the cell and then we put it into this vise here that is inside of a temperature controlled chamber. And we also include a load cell on top as we clamp down with the vise in order to know that we're applying a constant pressure throughout our measurement. remember that we saw that grain boundaries can contribute quite a bit. So if you consider densification, you want to be applying a constant pressure so that you know that you're not leaving like different gaps between your grains throughout the measurement, and in the process basically keeping that capacitance constant. So yeah, then when you actually move on to equivalent circuit fitting, there's a few different softwares you can use. You can use EC Lab, but again, this requires a biologic device, and it's quite useful. I don't personally use it. I actually use ZView. ZView is it's available online. I'm not sure if you need a license for ZView. I know you might need a license for zplot, which is basically a method of communicating with your frequency analyzer. But I believe that ZView is actually free. So you build your equivalent circuits, and in the process of building these equivalent circuits, we can fit them and then start to back out conductivities. And if we measure conductivities as a function of temperature, we can start to back out an activation energy for conduction. Fitting is probably the most difficult process of impedance spectroscopy. So it takes a lot of trial and error. Be patient with it. Read a good amount of literature in order to really be able to justify what kind of fit you are building for your model. If you can't justify your fit, then your fit's not good. You need to be able to say, why do I have all of these different components within my fit, and physically, what do they represent? So that's the end of this section. I'm going to move into case studies, but before I do, I wanted to ask again, are there any questions? No questions. Okay, cool. All right, so we're going to move into how we apply EIS to study batteries. Specifically, we're going to look at three different, let's talk about the advantages of using that technique first off. EIS is entirely non-destructive. You can basically take a battery off of the cycler, run a quick EIS measurement, put it back on the cycler, and you've changed really nothing in your system. Measurements can be pretty quick. There's a little bit of a caveat there, and it depends on your desired level of accuracy. If you want to take 1,000 points per frequency decade, or if you're only interested in taking 30, these things will differ in the amount of time they take, as well as the frequencies probed, right? So it's much easier to measure a bunch of points in the megahertz range than it is to measure a bunch of points in the millihertz range, and that's simply because a millihertz is slower than a megahertz. Usually though, at least for me, one measurement will take something like 3 minutes. The other possibility is to do these measurements operando. So like I was saying, you could be cycling your battery for quite some time and then run a quick measurement, keep cycling, run a quick measurement, keep cycling. And especially if you're using something like a biologic that can do both a potentiostat and a frequency analyzer, you can really sort of build that into your cycling routine. The other advantages here are that you can use it, on a full cell, a half cell, or you can even probe individual cell components with EIS, and you can learn a lot from them. As long as you're able to separate out different processes that have different time constants, you can really learn quite a bit about each type of setup. And then the final thing is that you can probe different conducting species depending on the geometry you actually use in your EIS setup. So one of the case studies we're going to look at does this, and hopefully we can learn there. So we're going to look at 3 different case studies. The first one is going to be looking at electronic and ionic transport in some cathode materials. The next one is going to be looking at how we can use EIS to basically learn about degradation mechanisms in full pouch cells, full commercial pouch cells. And then the final study is about understanding the impedance at an interface and using that information to basically better understand whether the interface between a solid electrolyte and a lithium metal anode is stable. All right, so the first study, like I said, is on the electronic and ionic transport in NMC 333 and 523. For those who might not know, NMC 333 just means a traditional cathode where you have 1/3 nickel, 1/3 manganese, and 1/3 cobalt. 523 means half nickel, 1/5 of manganese, and basically 1/3 of cobalt. So this study was interested in understanding the electronic and ionic diffusion properties at various states of lithiation, which really just corresponds to different states of charge. So if you want to better understand, how why your rate performance is maybe different in some areas than others, basically you might have more polarization in certain states of charge than others, then you can use these kinds of measurements to basically understand how electronic contributions and ionic contributions differ from one another. Now we need to be able to use blocking electrodes to isolate specific charge carriers in this instance, because if we just apply a normal, basically just put our pellet in the system, we're going to be measuring a mixture of electronic conductivity and ionic conductivity. And that's because these cathode materials are mixed conductors. They conduct electronically and they conduct ionically. So in order to measure the electronic conductivity, these researchers basically applied a silver paste to both sides of the cathode pellet. And the silver paste is only going to conduct the electrons. And when we put that then into our impedance cell, that silver paste is then in contact just with the stainless steel, which once again is just going to conduct the electrons. In that process, we are now probing exclusively electronic conductivity, because the only charge carriers that are getting to either end of our impedance cell are electrons. On the other side, when we consider measuring just ionic conductivity, we actually employ a few different layers. We put in our cathode here, then we put in polyethylene glycol, PEO, which only conducts lithium. So this is an electronic insulator, which means that electrons will not pass through this layer. Now we also apply a lithium foil on either side, and this lithium foil is going to provide the lithium to be able to cycle through our system. So now, because we are sure that we're not conducting electrons because of our PEO layer here, we know that we are exclusively probing the ionic conductivity of our pellet. So what these researchers were able to see is that as a function of the state of charge, they would see increases in the electronic conductivity, which initially, the first increase they attributed to nickel 2+ to 3+ redox. Remember that by losing an electron, you're basically creating an empty slot for an electron that can then quickly conduct, because you have more basically open slots for it to move through as you move through your cathode pellet. And then the further increase that they saw at higher potentials was attributed to cobalt 3+ to 4+ redox. On the diffusion coefficient side of things, what they see is a decrease with delithiation, which is very much counter to what they were expecting. In these cathode systems, because it's a layered compound, as you remove the lithium, the oxygen on either side of the lithium starts to see other oxygens a little bit more, and that 2 minus with 2 minus charge causes a repulsion. And normally you basically get a C-axis expansion of your material. You would expect a C-axis expansion to allow for more easy lithium diffusion through the layers, but instead they see, as we remove lithium from our material, a steady decrease in the diffusion coefficient of the system. And so what this suggested to them is that there are more subtle lithium ordering effects that play a role in limiting the diffusion of lithium ions through the system. Now, basically, what they were able to see especially is that there's orders of magnitude of difference between the electronic conductivity and the diffusivity of lithium through the material. And what they were able to conclude based on that is that the chemical diffusion, basically movement of lithium through your structure, is always limited by lithium ion transport rather than electronic conductivity. And that's really coming from the fact that they could see that as a function of delithiation, our electronic conductivity is increasing, and it's orders of magnitude higher than our ability to conduct lithium ions through our structure. And basically, just by using EIS in this way, they were able to see that this chemical diffusion is always limited by lithium ion transport. So the next case study I want to take a look at is a little bit different in the sense that the past study was really just focusing on cathode pellets. Here, what we're looking at is actually full cells. And what we want to understand is degradation mechanisms of these commercial full cells as a function of the temperature at which these are cycled. So what these researchers did is they cycled cells at room temperature at 45 degrees and another set that was alternating between 45 degrees and 65 degrees. They took impedance spectra every 100 cycles, and they also ran some post-mortem visual inspection of the electrodes and electrolytes, which just corresponds to basically taking apart the cell once it's dead. So what they were able to see in their initial measurements were two semicircles in their measurements. So we know that when we have two semicircles, that means that we have two sets of parallel circuits. And so what they fitted, and because we're starting here at a non-zero value of resistance, they added a resistor in front. So our initial resistor allows us to offset to a real value of impedance. And then our two semicircles allow us to fit a low frequency component and a high frequency component, as you can see. So then once they had that, they took again their impedance spectra every 100 cycles. And what they were able to see is that the high frequency semicircle, when we consider the degradation of both cells, all three cells, sorry, the high frequency didn't play as much of a role as the low frequency component really did. So what we're really plotting here is this resistance where our value for each component is basically increasing as a function of our cycle number. So what we see is that the low frequency component is the one that's really dramatically increasing throughout our measurement, and it increases even more when it's exposed to higher temperature. In the case of the high frequency component, we actually see very little evolution on the room temperature and 45-degree cells. We do see some increase on the 45-degree cell and the 65-degree cell. Now, the researchers took apart their cells later and were able to attribute each component. So the high frequency component, they attributed to the graphite SEI later, which stands for solid electrolyte interface. And it's basically just a layer, an insulating layer that forms on the surface of our graphite anode. The reason that they were able to make this attribution is because it only really increased significantly at a higher temperature. And what they believed was that the higher temperature was caused by increased reactivity of our electrolyte with the surface of our anode. On the low frequency side, they attributed all of these increases to the NMC positive electrode and charge transfer resistance through the cathode. And they attributed this based on continuous cathode mechanical cracking behavior throughout. As we crack our cathode, we basically make it harder for lithium to travel across, and we also add new exposed surface that can then react and insulate further. So based on this study, what EIS was really able to provide when paired with a post-mortem investigation was show where the primary degradation sources were occurring in this commercial NMC graphite cell. Now, what's really interesting about this is that now the equivalent circuit model that was built based on these cells can now be applied to these same types of cells, but active cells, and it can now be used to assess battery health. So you know that if you're at high values of resistance for this R2 value, you know that your cathode is starting to degrade, and you can basically start to potentially change the way you're cycling it in order to reduce that degradation. So the final case study that I want to talk about now is concerned with trying to assess the chemical stability of lithium indium chloride solid electrolyte material against lithium metal, and try to understand the conductive properties of that interface. The reason this kind of study is really interesting is because solid electrolytes are a way to potentially incorporate lithium metal into solid state batteries, which would allow for huge capacity and lifetime gains. The huge problem with that is that that requires a stable interface with lithium metal, and that is difficult to achieve. So the way that this study was conducted was first to use XPS to assess chemical reactivity, and then use EIS to probe the conduction properties of the lithium indium chloride, which I'm shortening to LIC, when it's in contact with lithium metal. On the XPS side of things, the initial spectrum that they see at 0 minutes is just lithium indium chloride. After some time, where basically a sputtering gun is used to shoot argon, ionized argon onto the surface of a lithium metal, a piece of lithium metal that is then deposited onto the surface of the sample. What they see is changes in the indium 3D lines, where they start to see the appearance of indium oxide and the appearance of just pure metallic indium, which corresponds to indium 3+ being reduced to indium 0. And so this is basically very clear evidence of interfacial evolution and formation of what we call an interphase. An interphase is whatever phases or mixture of phases starts to appear at the interface between two materials. So then we use EIS. Now, EIS first has to be used to probe the ionic conductivity of just the LIC alone, so that they can establish a baseline. And then from there, what they start doing is building symmetric cells, where they put the LIC in contact with lithium on both sides, and they assess the evolution of the resistance as lithium starts to react with LIC. We know that that'll happen based on the fact that we've seen the XPS results. 3 semicircles were required for that fit. I'm running out of time, so I'm going to start moving a bit faster. What they really see in this system is a steady increase in the impedance as a function of time. And so this is a clear indication that the interface that's forming between LIC and lithium is very resistive and is not, and it's proof that LIC is not compatible with direct contact with lithium metal. So overall, I just want to summarize a quick key points. EIS is a really quick and non-destructive method of probing all these different electrochemical processes and conduction processes. What's really nice is you can isolate resistances from different portions of your system. And past that, you can apply it to a lot of different sample geometries. With that said, you have to be careful about your equivalent circuit fitting, and you need to be very reflective about that process. So thank you so much for your attention, and I'll happily take questions.
Sorry. Hey, great presentation. I just had a quick question about the first case study where you were talking about using the polymer versus the silver to isolate the different contributions. But if we, like, I guess I'm a little confused because in the high frequency domain, where maybe you're looking at like the bulk conductivity, I don't see how like changing the electrode is going to stop you from moving like electrons or moving lithium within the bulk of the material. So how do you like isolate those different contributions in that case just by changing the electrode?
So you need to, right, if we want to measure a current, that current needs to go all the way through our system, right? So it's really these interfaces here that are allowing us to block whatever conduction we don't want to measure. So we know that if we measure a current, that current is going through our system, and our lithium is not going to move across this interface. With respect to the exact frequencies that are measured, I'm not 100% sure what the frequencies they measured were, unless they're not given. I'm not exactly sure what those frequencies were, but it's really about,
well,
yeah.
Yeah, no, that makes sense. But I guess my question is, well, you know, like people use like, I guess even in some of your other examples, like you can use when you're studying solid state electrolytes, for example, you can use like gold blocking electrodes, and still when you do impedance, you're going to get, for instance, like a semicircle which corresponds to your bulk conductivity, and then like some kind of blocking low frequency feature. So in that case, like I just don't see how using silver in this case is going to stop you from seeing any ionics like in the bulk. I guess is what's confusing me.
Yeah, it's a good point. Yeah, no, because it's true that those types of systems or those types of gold blocking electrodes are used often in solid state electrolytes. I think that part of the reason there might be the different orders of magnitude. That in this case, that they really might still be measuring some amount of ionic conductivity, but when you consider the orders of magnitude that they are measuring as far as their electronic conductivity goes, that they might be diluting that. Commonly in solid state electrolytes, what you will do first is assess the electronic conductivity, and once you'll measure, and then you'll also measure the electronic conductivity potentially with just a DC polarization method. And when you do that, you can usually see that your electronic conductivity is really orders of magnitude smaller than your ionic conductivity. And when you do that, you can basically then assume that most of the conduction that you're actually observing in the impedance spectra is coming from your ionic contributions rather than your electronic contributions. But with respect to actually blocking, it's something I need to spend a little bit more time understanding.
Okay, gotcha. Yeah, I think, yeah, I guess it kind of depends what feature of the Nyquist plot they're looking at here when they change electrodes. But I guess I don't know. But thank you.
It's a good point. Thank you for bringing it up. Any other questions? All right. Well, with that, I'm going to